University. Andrei received a Fields Medal in 2006 because of his results, which were bridging together representation theory, algebraic geometry, dynamical systems, combinatorics, everything. Yeah.
Abbi pazienza, non è partita la registrazione. Se aspetti un attimo la lancio e fai la presentazione, così resta anche vista.
Ma comunque, sure.
Grazie.
No worries. Sorry. May I start?
Yes, you can. Please. Go ahead.
Thank you. So once again, it's a great pleasure to have here ANDREI OKOUNKOV from Columbia University. ANDREI OKOUNKOV received the Fields Medal in 2006 because of his contributions. We're starting from rep theory to algebraic geometry, bridging everything also with math physics, dynamical system, combinatorics. And so today he's gonna tell us about Lie theory without groups. Please, Andrei.
Thanks, Martina. Thanks, Alfonso. Thanks, everybody, for joining this discussion. This will be, I hope to have made it more kind of fun than formal. So you'll see. So not to insult your intelligence, but a definition of a Lie group is when you have a manifold which is also a group, and it's kind of it's important that you have these two different structures interacting. I mean, it's like you have like the sun and the water that together made plants blossom. And don't read too much into this correspondence between different series of Lie groups and the different flowers, except maybe the Plashen flower really does resemble G2 root system. So that's anyway. All Lie groups have been classified, and well, I teach a class on Lie groups at Columbia. You know, it's fun and kind of. I hope the students get the sense that that Lie groups are really everywhere, and then when you get to the end of the class, they discover, okay, the Lie groups have been all classified, and kind of the world has been explored and has been inhabited, and there is somehow no more. And so for a long time, many Lie theories have been searching for what are the new worlds, and okay, people have different ideas. I'm not claiming that this is what I'm going to present in this lecture is really it's really the only or the best. You know, Victor Katz and I have been joking about what is the Lie algebra of the 21st century and so on and so forth. But anyway, so many people have been searching what should Lie theory be now, and I will talk about one particular kind of incarnation, and this was really very strongly influenced by applications in mathematical physics, concretely in supersymmetric gauge theories and similar theories in 2 and 3 dimensions, 1+1 and 2+1 dimensions. It's also an algebraic geometry, and this is meant to be a talk for kind of broad audience. So I don't want to motivate it from core. You can motivate it from kind of core questions in Lie theory, but I'd like to take the more applied approach. So maybe from the point of view of special functions, which is one of these kind of applied directions in which Lie theory reaches to the rest of the world. And so I'll start with a brief summary of the classical theory. Okay, let's see if this is scroll. Oh yeah. Of course, I can't summarize the classical theory. The theory is very, very old and has many, many chapters, and there are many, many people who contributed to the development of this theory and still contributing. How you can don't take this too seriously. This is all meant to be just fun. So people still contributing to this to the development of the theory today. So hi Victor, hi Karada, and I think there's also Claudio somewhere, so he should be also there, and many other people. So anyway, so this is a Lie theory is very, very rich, but I'll start with a very kind of basic example, and that is the representation theory. Its origins was really was going hand in hand with harmonic analysis and homogeneous spaces and related special functions. It may be the first special function a student in like electricity or magnetism or quantum mechanics sees, the spherical harmonics. And I wish the students were taught this in a modern way, but they aren't. But in case you think spherical harmonics are something very complicated, well, the way Lie theorists sees spherical harmonic is think, well, what's a sphere? Sphere is a homogeneous space, and you can realize it, for example, as the Riemann sphere. So that will make it homogeneous space of SU2, so 2 by 2 special unitary matrices modulo diagonal matrices. And then very generally, functions on any group are just the matrix of the harmonic analysis on any group, on any compact group is beautiful. And in that the functions are just decomposed into a matrix coefficient of reducible representation. So you write your group as in all possible reducible representation, take the matrix coefficients, the functions, so that's the decomposition. So if you're looking at SU2, those are very, very simple. So there's one irreducible representation of each dimension, namely you take polynomials, SU2x and polynomials into variables, just from acting on the plane, and you take polynomials of fixed degree. That's the complete list of reducible representations. And now if you're looking for, if you're doing functions on a homogeneous space, means you'd like your function to be invariant on one side by a group, means the corresponding vector has to be fixed by the subgroup. And okay, if you're looking at polynomials of fixed degree d in x and y, then what are the vectors that are fixed by diagonal matrices? Those exactly the kind of monomial of exactly balanced, so x times y times d over 2. And those are the matrix coefficient that have all this vector on one side and any other vector on the other side. Those are the functions on the sphere, and those are exactly the spherical harmonics. So, and then similarly on the n-dimensional sphere, we could be looking for, for simplicity, we can look for one particular function, which is the radial eigenfunction of Laplace operator. So that means it's invariant by the subgroup H on both sides. So it's not just a function on the sphere, but also what stabilizes a point. So this is taken for rotation. Radial means it's invariant under what stabilizes a point on the sphere. So you're looking for functions now in double cosets, means you take the group is S and rotation in plus one dimensional space, and what fixes a point are rotation in n dimensional space. And so this is that particular matrix element will be a radial eigenfunction, and it has a remarkable form. It has it's given in terms of the Gauss hypergeometric function, and where the parameters are, one parameter is the dimension of the sphere, and the other parameter is the number of the harmonic. And so we'll be talking. So this is kind of the first special function, and maybe the first and more or less the first and the last special function we'll see today. But so this is, and I want to stress that this function is really well. I don't know. I don't know how you feel about hypergeometric functions, but it certainly our forefathers were mesmerized by this kind of things, and maybe we should be too. And so first of all, this function satisfies second-order differential equation, and it generalizes the radial part of the Laplace operator on the sphere, and in particular interpolates in dimension. Like I said, one parameter, which is just arbitrary complex numbers, if you want, in this formula that if you specialize it, you get to n-dimensional sphere where n is dimension of the sphere is arbitrary. And then second, this on the sphere, compact thing, then you have to set the other parameters. It's a number of harmonic. So that number you set to be 0, 1, 2, and so forth. And with this choice, if you look at this kind of factorial power, with this choice, the series terminates. So you get, well, corresponding to the fact that the reducible representation of finite dimensional. But if you take a general parameter, this will be still representation theoretic quantity, and it will correspond to infinite dimensional of representation of some groups, and so it's also pretty nice. And I want to stress again that it's sort of remarkable that this is the series for this. If I write a general second-order differential equation in X, then of course I can solve it. But there's no reason for each term in this series to have such a beautiful factored formal parameters. And similarly, well, a series, if you think about it, a series is just as a series as an integral is more or less the same thing. So this is this beautiful concrete series for hypergeometric function. There's also very nice integral. There are very nice formulas for the value of this series at x equals 1, first read by Gauss also. There are formulas for the monodromy of this differential equation. Formulas. So this is a solution of a second order differential equation on X, but there are commuting difference equations in all parameters A, B, and C, and they're also explicit. And they all have, and all of this fact have a representation theoretic meaning, have representation theoretic proofs, and also, of course, used all the time because these are really functions that appear in really matrix elements of reducible representation, and so on and so forth. And so the Gauss hypergeometric function, that's the rank 1 case of more general special functions called multivariate Jacobi polynomials. And they were associated to an arbitrary root system by Heckman and Obdam. And then what will be important to us, there's a Q difference handle where instead of in X we had a differential equation, and in Q we had here in X we have a differential equation, and A, B, and C we have a difference equation. Means if we changed A, B, or C by 1, something happens. But there is a Q difference extension of the whole story where everything, both the differential and the Q difference in the difference equation both become Q difference equation. It means you take X and you multiply it by Q, where Q is some number. So that's and so this was of course pioneered by MacDonald, and then from the technical standpoint transformed by Cherednik, and that of course has millions of applications, starting from the fact that this MacDonald world of special functions covers both real Lie groups and p-adic Lie groups, and then of course that also finds application very far away from the core Lie group theory, like people there's a large group at MIT, a large group here at Columbia that apply the magic of MacDonald polynomials to study things like interacting particle systems and other very classical problems in probabilities. And also another thing, if you also look at the hypergeometric equation, it's also the simplest instance of the Knizhnik-Zamolodchikov differential equation in conformal field theory. And that also has an important Q difference in deformation written down by Frankel and Rashetikhin. And their Q difference has a really concrete meaning that, so conformal field theory, it's a field theory, means it tells us about the continuous limit of some phenomenon that could be happening on a lattice, say. And the QKZ, it's the equation that corresponds to this Knizhnik-Zamolodchikov equation on a finite lattice, so finite lattice step. So that's very important. So this integrability of lattice theories. That's QKZ. It's stations. So and this, of course, these are very general equations. They encompass millions and millions of applications, but they're still rooted in the classical Lie theory in the sense that the root systems, they really imprinted there. There's some, like if you take this Cherednik theory, there's a root system. If you take Knizhnik-Zamolodchikov equation, there has to be a representation of basically of a Lie group, or maybe concretely of some quantum group, but it's basically a Lie group representation. And so this is these are very general special functions, but we have not gone very far from the world of Lie theory. And of course, if you just want to study linear differential equation, linear difference equation, there is a general theory of that such, and it's a theory of D module, differential module, and you can ask many questions, like questions about monodromy, like monodromy is a linear differential equation. You have its corresponding monodromy, there's some map. You can study that map, and also the equations we studied have to do something with representation theory of some very specific objects, groups, or maybe Lie algebras, or you're also developing algebra. In principle, you can study representation of general associative algebra. That would be something to study too. Also very important. But it's very hard to find places where both things intersect. So it's hard to find place where this sun and the water can they both exist together and give something, you know, like a habitable, fertile place to live. Because it's if I give you a general, if I give a general differential equation, linear differential equation, you know, you can study it, but you won't be able to say much about it. It's like I give you a random real number. You know, what can you say about this real number? You have to be, if you have some other way to talk about that number, that will be a different story. And well, what I want to say, the point of the talk, there's a whole galaxy of new possibilities where, and that's stimulated by modern high energy physics, where two different points of view, or maybe two or more different points of view meet, and really create some place where the vegetables can grow. I think in this side galaxy, I think hard to see the Earth, but it's there, where at the end of this arrow, and that's where now we're going. But in fact, that's what I'm trying to say. This root vegetables that we were growing on Earth before, they exist. You can grow them in all of this galaxy. And so what is them? So and then of course you can. I mean, it's hard to pinpoint, but maybe I'll just take a personal point of view. I mean, for me personally, that was very important. That I heard from Nekrasov-Shtashvili. That was a couple of years before they published their paper. That all of these functions we just discussed, should be in fact special cases of functions that count holomorphic maps from Riemann surfaces to some variety X. So you think, I mean, there was somehow nothing of the kind in our discussion yet. There were no algebraic varieties, there were no Riemann surfaces, no holomorphic maps, no idea of counting them. But of course, in the theory of, broadly speaking, Gromov-Witten theory, people have been studying these objects for a long time, and maybe I should pay special tribute to Boris, who so tragically passed away last year. Since Boris has been important, very important, both for Russian and for Italian mathematics. And, we should particularly highlight his contribution to the subject. And so, what is this about? So, first of all, I want to say, right before I say this, anytime that this it will be difficult for me to. It's impossible to make exactly the just attribution, because the scientific discovery is self-similar, meaning you're in a boat and exploring some universe, and you find the first piece of land, you think, wow, great, and then you discover that this piece of land is a part of some archipelago, and you're even maybe more happier. But then the next person comes and discovers that this, in fact, archipelago is connected to a continent, and then so on and so forth. So this is at every step you can say, well, this was a decisive step. But anyway, so if I decided to call it. I decided to associate the most decisive step with Nekrasov-Shtashvili. Of course, anybody can have their own point of view. And so, what is this about? So, in algebraic geometry, it's a very, very classical question, that's exemplified by the 27 lines on the cubic surface, which you can see there in the background there. It's a very classical question to study, to count algebraic curves of such and such genus, such and such degree, that belong to sitting on some algebraic variety. Like for instance, if I take a cubic surface, that's not cubic surface, with 27 lines on it, that is to say curves of degree 1, and then of course they'll be automatically of genus 0 too. And then, so other famous examples, if I fix 8 points in the plane and I ask for a rational cubic curve to pass through them, there will be 12, and so on and so forth. So those are very classical questions that go back to, of course, the 19th century, and so in a very different development in mathematical physics, if we talk about the state of some very, very large physical system, then so this would be okay. This is, I admit there's a while the picture looks similar from the previous transparency, of course that's a big leap, but anyway. So let's talk about like the air on the planet, and here's a temperature map for a planet. So it's a kind of really big system. And then, well, we can imagine that any local parcel of air, like like the one I'm holding between my my hands now, that in some equilibrium, an equilibria of local equilibrium of air are described by in fact 2 parameters. In fact, so that'll be like the pressure and the temperature. And so this means the state at every point in the space, I have a map to, in this case, 2-dimensional manifold, namely the manifold of lowest energy states, vacuum state, and so on and so forth. And so, but then these parameters, they can vary from point to point. And so then I really have a map from my space to the space of vacuum. That's kind of like a modulated vacuum. And so, for instance, in the weather map, you can see the temperature or the pressure. Weather map is what? It's a map from a 2-dimensional space to some other manifold, which in this case is also 2-dimensional. Then this means you can do, if you want the weather report at a given place on Earth, that will give a temperature and the pressure. So, well, those will also give direction of the wind, but this is some direction of the wind that depends on the coordinates. I mean, it's like the coordinate system, how they are moved with some inertial coordinate system. So this is, and so then this in the presence of supersymmetry, this counts what we discussed before. In the presence of supersymmetry, the target and the source of this map, there could be complex manifold, this extra structure that's manifestation of supersymmetry, and the counts we were discussing before, they could be interpreted as indices of involution operators. And so if you think of an involution operator in the supersymmetric system, in the supersymmetric quantum field theory, it's like an infinite dimensional version of a Dirac operator, and that you can ask what its index, and this index would be supported on supersymmetric maps, that is to say holomorphic maps from your source, which is, I think, of course, now of course the algebraic, our air is not supersymmetric, but you can imagine in supersymmetric situation, the surface of the Earth would be considered a complex manifold, and the space of possible states of the weather would be complex manifold, and the supersymmetric map would be in particular be holomorphic, and so then this is counting this holomorphic map. This would amount to computing the index of a certain infinite dimensional Dirac operator. And the index operator, of course, is very important because it's scale invariant. And in particular, while we're talking about if you compute this index for a very, very large system, it's the same for a very small, for a system of any size. And so you can, this approximation that we say a system is very large and therefore could be described by modulated vacuum, that approximation for the index is true literally. So this means you don't have to take any limit. It's true for index. It's true for any size. Anyway, so a index. So now I forgot to say, or maybe I will say now, it says on transparency, that this index of an operator is really a vector space, or virtual vector space. And so it carries a virtual representation of the symmetry group involved. So in particular, the transformations of the source and transformation of the target will act on that space. It's a virtual representation. And moreover, it will grade it further. So the map has a degree. And so this index is further graded by the degree of the map. It's grading by the degree of some lattice. And then degree of that lattice, that lattice, it's convenient to interpret as a character lattice of some torus, we call it Kähler torus. So altogether, you have a representation of some graded vector space, whose graded component, graded by degree, or by the characters of the scalar torus. And this graded component, since the space of holomorphic maps from the space of holomorphic maps of given degree is a finite dimensional manifold, and so that would be each graded component would be reasonably well. I mean, it doesn't have to be finite dimensional, but it's you know, kind of reasonably understandable representation of this symmetry group. Okay, that's the object. The object is that index we think of this as a representation of the symmetry group, the source and the target, and further it has a gradient by degree, and this is and kind of to maybe to whet your appetite from the beginning. It's very it's amazing that in the symmetry, the two kinds of variables, the ones which respond to the action of the group and the ones that keep track of the degree, they're sometimes very often can be exchanged by something like a, well, we'll see, it's like a Langlands duality first observed by Ventriligator and Zedek. So now our Q hypergeometric function, so now this I've written now the Q analog of this hypergeometric function, that is where it's the same kind of expression, except instead of factorial power, I put this Q shifted factorial power, so instead of a to the d, I write 1 minus a, 1 minus qa, 1 minus so forth. This very, very basic object that appears in the simplest possible instance, when the source is really the Riemann sphere, this automorphism over the sphere is what's a rotation. So rotation is a number, q, which we might as well complexify since the sphere is complex. So it's like a complexified rotation, q is in c star. The target will be just t star p1, cotangent bundle to p1. It also has two automorphisms. One automorphism A that scales the p1, and then the other automorphism, which is called h bar, that scales the cotangent directions. And so this would be, so these are the group elements. So the group elements q acts on the source, and A and h bar act on the target. And then I have the grading by the degree, and so I put z to the degree, and then for given degree I get since my target space is not compact, you get an infinite dimensional representation, but this infinite dimensional representation has a well-defined trace, and namely given this by this rational function. It's not a hard computation, but that's a computation that tells you that this object we saw before as the kind of the most corresponding to the most important, the most basic homogeneous space, namely the sphere, is now corresponds to the most basic target which we can imagine. So this with the kind of supersymmetry we want, we need the target to be holomorphic symplectic, and so it's hard to imagine a holomorphic symplectic variety which is more basic than T star P1. Now this T star P1, well, you can think about it many different ways. It's the metaphor I want to use is that this is like the unicellular organism of the. We had this metaphor of watering the plants, and then this is like one cell. It's not a plant yet, a unicellular plant. And this is T star P1. It's one of the many things you think it's natural, and it is that, for example, that's just a resolution, the blow up of the usual quadratic cone. It's also that cone is also the set of nilpotent elements in the simplest possible D algebra SL2, and it's this resolution, which is blow up, T star P1 is blow up of the cone. That's the simplest possible instance of the fact that T star G mod B resolves the nilpotent cone in general in algebra. And from the physics point of view, it's really more the singularity is more important than the resolution, but that's maybe let's not paddle on this too much. And now the way this is going to be this kind of important slide number 1. The way these cells, this kind of unicellular guys, fit into the general plant, and here this is slides of a pine tree here, but it's so this is described by 2 periodic hyperplane arrangements, and this generalized the root data of the Lie group. And you can say, well, what is the meaning of this arrangement? And I can, in terms of the Q difference equations that we're talking about, this is very easy. Those are just the poles. I mean, those are just the singularities of the equation. The singularity of the equation, they live on 2 different tori. There is a torus for the scalar variables, and there's a torus for the covariant variables. There's a torus for A, and there's a torus for Z. And if you look at the singularities, they're in fact like a subtorus arrangement of subtori in this tori, and if I unfold this on the plane, then I get a periodic hyperplane arrangement, two periodic hyperplane arrangements. And so this would be the equations I will call root, and the hyperplane arrangements are given by the facts. So I have maybe a complex torus, torus Z, and then my hyperplane arrangement is where the root vector pairs with the logarithm Z, and the pairing is integer. And since this pairing is required to be an integer, it's a periodic arrangement. But maybe I'll stress from the beginning, this is not a homogeneous. This is in contrast to the usually that hyperplane arrangement is not homogeneous. There's no reason for a symmetry group to act transitively or anything here. So that's right. So you can again, one can discuss these definitions from many different angles, but from our angle, those are just the singularities. Okay. And going back here, sorry, I should say, then this is going back here. This has one singularity in Z and one singularity in A. And so this will be 4 days. So it will be the usual arrangement. Means the SL2 arrangement is just you take just integers on one side and integers on the other side. So and the singularities are roughly, not roughly, the singularities are at Z equals 1 modulo H bar and A equals 1. Maybe I should put that. So, and now I want to, what's the relation to the usual definition of roots is that, and corroots in Lie theory, well, if you're familiar with the definitions in Lie theory, then the roots by definition are the weights of the action of the you take a maximal torus A in subgroup G and make it act on Lie algebra, and the weight of that action are the roots. Those are the same as the weights of this torus action on the tangent spaces to fixed points in this X with this T star G mod B. So for general Lie algebra, instead of T star P1, you take T star G mod B. And if you look at the fixed points of the torus and you look at what are the weights and the tangent spaces to this fixed point, those will be exactly the roots. And very generally, this is discussion of this. This gives you the definition of where would be the singularity in the difference equations. For any X, this is a recipe. You follow it, and you get some hyperplane arrangement. Now, also in the Lie theory, the core roots of a group have to do with some special maps from SL2 to G, some special cohomorphism from SL2 to G. And then if we project this to G mod B, you get some special curve classes, some special P1s into G mod B. And those are the Keller roots. So in general, if you want to describe the poles of the Z variables, we're counting degree of the map. And if you'd like to describe the poles of this equation, those are special curve classes. So this is, and maybe I want to say that the equivariant and the Keller roots are in principle things of different nature. Like, for example, they live in ranks of different, in lattices of different rank. There is no reason for the H lower, the degree is counted by H lower 2 of your variety X. And that lattice has nothing to do with automorphisms of X in general. So this would be, but that Langlands-like duality of interligator and Zybrick, which I referred to before, that in fact exchanges it, which is pretty amazing. So you take what was these two lattices, they go one to one another. And so then moreover, this arrangement is not just a picture. There's something attached to every wall, and namely for every wall there is an operator. And what is that operator? Those are we're talking about Q difference equations, and those are the singularity. And this operator is like the multiplicative residue of this Q difference equation. I don't want to make a more precise definition, but you can imagine that if in a differential situation we have a pole, we can take a residue, then similarly in a Q-difference situation, you can define what it would mean to have a Q-difference Q residue, and that will be an operator that sits on the wall. So, but those operators naturally form a groupoid, namely the objects in this groupoid are the alcos of this arrangement, the maps are the operators themselves, and then the relations are the codimension 2 strata, the relation being that if I go around a codimension 2 strata, then I come back to where I started this. And so this very simple definition, right? And also since it has to be the polar part of some equation, that it depends on the variables in a very specific way. Namely, if my wall is given by a linear equation where some root alpha paired with log z plus n equals 0, it's a linear equation describing my wall. And then I'd like my wall operator to depend on this variable q to the n z to the alpha. So that makes sense. And then if you think about this kind of very basic structure, generalizes like a million other things. Like if you think about how the affine Hecke algebra acts, and how the Chirag-Neak operators are constructed, they're all constructed this way. And also, if you think about what's the Young-Baxter equation, the Young-Baxter equation is an equation, first of all, with the spectral parameter. But the spectral parameter means it depends, so you have just the A2 arrangement. Each variable depends on the corresponding equation, so you get like R1, 2 of Z1 over Z2, and so on and so forth. And the condition that they multiply in the two different ways, and this is the condition that that's the Young-Baxter equation. So this is one piece of data, and maybe I want to stress again that this is we're doing Lie theory without groups, and in particular there is no group here. It's just a groupoid. This arrangement is not transitive. There's no reflection symmetry. There is a translational symmetry, but that's kind of really pretty weak. But I mean, it is important that there is a translation symmetry, but that's so there's no group action. It's just like it's a group. But it does give all the structures we really like in quantum groups and in other places. And maybe you can ask, what's the very first example of this new space X? I should have maybe given it before than here. Maybe I should have reordered my slides. Then it's the very first example is the Hilbert scheme of points. So the Hilbert scheme of points is what? Is the singularity singularity is a symmetric product. So if we're talking about the Hilbert scheme of points in the plane, the singularity is a symmetric product, and unordered n tuple of points in the plane. And when the Hilbert scheme of points remember, it's a resolution of the singularity. It remembers the extra information, namely it remembers the actual ideal in the ring of polynomials. So it remembers which polynomials were vanishing at a given point. So the Hilbert scheme of points are the parameterized ideals of codimension n in the ring of in polynomials in two variables, and then if I forget the actual forget the ideal, I just take the support of this take the support of the set defined by cut out by this equation, counting multiplicity, and I get a map to the symmetric product. That's the resolution of singularity. And there are, of course, many more examples using among Nakajima varieties. And this is what we discussed before for the Hilbert. What are the data that we the data that we discussed before for the Hilbert scheme? First of all, what's the analog of the hypergeometric function? The analog of the hypergeometric function, of Q hypergeometric function, it's like the Q hypergeometric function, but it's the constant term, not one. The constant term already itself is like Macdonald's polynomials. And then those are important functions because they're basic building blocks in various curve counting theories in 3 dimensions. So this is also, since this is the simplest possible, this is the simplest example beyond the classical theory, it has to be self-dual because the dual will be another simplest example, so it is self-dual. And the roots, both equivariant, since self-dual, both equivariant and Kähler roots have to be the same. And they're in fact given, so if I take in the Hilbert scheme of points, of n points in the plane, the roots are 1, 2, 3 up to n. And so your arrangement are the fractions with denominators at most n. Interesting arrangement, but it's not, like I said, it's not transitive. It has translational symmetry, but that's it. And the corresponding groupoid is something which is beautiful. It can be written explicitly. It's something kind of like the quantum while group for double loops. So this is the explicit formulas will take us maybe too long to write, but it's something it's some interesting thing. And in fact, we did this computation for all Nicogen horizon, but in particular for the Hilbert scheme, we did something pretty explicit. And maybe one more piece of data I want to say here, that if you don't like walls, and I'm counting myself also among those who are maybe wish for a world without walls, then you can take all this wall data and make one big nice matrix out of it. Namely, you just multiply. So it's a groupoid. You can multiply them in arbitrary order, going from choose a path that goes from some kind of minus infinity to plus infinity, and multiply all of your matrices in arbitrary order. It doesn't matter since it's a groupoid. And so that would be like the monodron. That matrix was some elliptic matrix, and it's the monodron of the corresponding. So instead of having countably many moles, you just had one matrix, which is the elliptic matrix, because it's the monodron of the corresponding Q-difference equation. And this matrix of the elliptic function is really really well understood geometrically, because it has a direct description in terms of elliptic homology of your original x. And so this is what we did for those two kinds of variables. There's the first different variables is my paper was MIUR wrote down, and for the Keller variable, that's relatively recent. So there is a way to package all this information in something else, and to say, I'd like just give me one elliptic, or maybe two elliptic matrices, meaning one for the Keller, one for the covariant, and this will be exchanged by this Langlands duality. That's another way to think about it. And now, so this is we've seen one kind of visual image of the world without groups, and this is this dynamical groupoid. And then there's another geometric object which I'd like to maybe use to illustrate what this world without groups looks like. And that's let's go back to this nilpotent cone and then ask what are the meaning of other, so nilpotent matrices, what's the meaning of other matrices? The other conjugacy classes, they'll fill the whole Lie algebra SL2. And the other conjugacy classes are deformations of the nilpotent cone as a symplectic singularity. And similarly, if I have a general X, I have a very similar picture. I have my general X, and I study the total space of its deformations. There would be some Poisson variety which generalizes both the Kirillov constant Poisson structure on the Lie algebra. It has also generalized depending how these different leaves, depending what sort of X I take and how different leaves fit together. This will generalize all both the Lie algebra situation, Boston Lie group situation, and also elliptic versions of that. And I wasn't planning to go into a deep discussion of this topic, but maybe I'd illustrate in terms of the Hilbert scheme. I'll illustrate what's the difference between kind of the Lie algebra Lie group and elliptic situation. And then let's an excellent example of such Poisson manifold is if I take the Hilbert scheme of a rational Poisson surface. For instance, I can take P2. So P2 has many Poisson structures, depending is given any cubic polynomial gives you a Poisson structure on P2, and depending on what the corresponding cubic is, I get different structures of leaves. So this is so if I have the Hilbert scheme of a Poisson surface, what are the symplectic leaves in there? The symplectic leaves are parametrized by which points got into the zero divisor of the Poisson structure. So if I have my Poisson leaves are parameterized by points on this cubic curve. The cubic curve could be a triple line, could be a rational cubic, or could be a non-singular cubic. And then you see that in the two latter cases, for instance, the Poisson structure has a simple pole, simple zero. Simplicity form has a simple pole along the along the corresponding. So your axes are your individual axes are locally aveyous, and then in the closure of a given leaf, the leaves in the closure of a given leaves are parameterized by either a rational curve or an elliptic curve. And so that would be this would be, can you see my cursor? This in the upper in the triple line will be like the Lie algebra case, it'll be like the group case, and that's the elliptic case. All right, so also I want to say at the end that while I was stressing, sorry, that's a 2020 COVID. If I was stressing the more special function thing, but also there is the representation theory side of thing. So all these functions, they really have to do with representations. Namely, there's a very tight link to actual representation theory. Namely, the spaces of maps, or appropriate K group of the space of maps, is a representation of a quantization of X check. Just this. So this is maybe Coyote is the person to credit with the physical insight, and then there's a very deep and detailed study of this phenomenon by Braverman, Finkelberg, Nakajima, and many combinations, many followers of that. So this is this. And if you'd like, what is the actual enumeration, the actual Q hypergeometric function type of thing, the Virchow function, the actual enumeration, that in fact, that object you should think of as a refined character of this representation in the spirit of this Nekrasov's QQ characters of representation of quantum groups. So QQ characters are not unlike this Nakajima's refined QT characters, but they are more flexible in the way that they. So the QQ characters, if you have a geometric realization of some representation, then the Q2 in the QT character, you remember the cohomology of the corresponding space, whereas in the QQ character you more look at this just the cohomology of the sheaf of differential forms, something like that. So that's okay. Maybe that's a little too detailed. Of course I can't. And this is a very long subject, and there's only so much of it I can squeeze into a 1-hour lecture. I started. So first of all there's old recordings. We had a winter school in Jerusalem a couple of years ago. So there'll be now 3 years ago almost. And so there has this video recording, but also out of sense of altruism, I guess, I've been teaching an extra course on this sort of thing starting, and we started with we started in May, and that still continues. I hope it will be wrapped up before Christmas. And that's you can if you look to my webpage, you can find information there. And so it's this is just this. I mean, of course, even the course that's been going since May cannot really fit all the information in it. But there's lots to learn, and maybe I'll conclude with this kind of visual image what the world without Lie groups might look like, and maybe I'll stop here.
So thank you, Andrei, for this very nice lecture. So is there any question or comments? So if you have questions, please feel free to unmute yourself and ask the question, or write in the chat. I can read.
So maybe I'm curious, just so Andrei, since you were saying that you have, I mean, you convinced us that there are all these analogs of Val groups and Hecke algebra, affine Hecke algebra, and so on. So for affine Hecke algebras, do you also have, I mean, some sort of duality, some involution, and some sort of causal-Lucy basis, or something like this? Can you?
Yeah, that all stuff exists. So then you can you have a there's a Cartan-Lustig theory for. So this is so maybe I should have said this. So here, right? Maybe I should stress here. So this in this setting, you can really talk about geometrically what is the Cartan-Lustig theory supposed to be like. For instance, this is so Roman Bezrukovnikov and I, we've been talking for years, and maybe this year we'll finally finish that paper, which has to do with what this sort of thing has, what this kind of curve counting has to do with representations of representation of quantization characteristic P. However, once we finish this paper, it is already clear that there's something much more natural that you should do, namely, of course, representation and characteristic P. That's wonderful, but since we're doing unspecified, very large unspecified P anyway, you might as well do quantum groups as roots of unity, and quantum roots of unity that is directly interpretable in this language. So what is the different kinds of module, the standard, co-standard, irreducible, tilting, all of them have their names in this language. And so the relation between what this groupoid has to do with Cartan-Lustig theory, that is very direct. So I'm very grateful for you, Martina, brought this up. This groupoid really does Cartan-Lustig theory for this kind of slightly funny algebra, but they're not so funny because the quantization of the Hilbert scheme, that is a Chernykh algebra, or rather that's the spherical subalgebra of Chernykh algebra. So Cartan-Lustig theory for that is really done in terms of that funny groupoid.
Yeah. Thanks.
Sure, that's an excellent question. Thank you.
Any other comment or question? Okay, so if not, let's thank Andrei again for this very nice talk.
Yeah, that was my pleasure. Thank you guys for inviting me. I wish I can come see you in person.
Hopefully soon.
Yeah. All right. Thank you so much.
Grazie, Andrei.
Okay, so if you have questions, unmute yourself and ask now. There is no recording, I guess, now.
Okay, I'm switching off the recording.
Okay, now there is no recording.